welcome back to Math 256. This is Scott. Let's get started. So, in the last section, we made a new acquaintance, and that new acquaintance was Laplace transforms. But as of yet, it has not proven to be anything useful to us, and in fact, it's just another chore. So now we're going to figure out how to make those Laplace transforms work for us. So, 6.2 has to do with solving initial value problems using our newest tool. So solving initial value problems. All right. Well, first off, let's get some legal technicalities out of the way. So a function is piecewise continuous if it is continuous at all but a finite collection of values. Okay, there we go. Now a function is exponentially bounded if there is a value C such that the limit as t approaches infinity of e to the negative ct f of t equals 0. So exponentially bounded means that essentially this function is not going to end up being in the long run bigger than any exponential function. So this would include essentially every example that we've ever seen of functions. So some types that would not fall into this category would be ones that involve vertical asymptotes of some kind or another, or like, in particular like tangent, for example, or else weird things like maybe factorials or something. But among functions that we would be finding as the characters in differential equations, this was typically always guaranteed. Okay, so here's the setup then. The setup. We're going to assume that f is piecewise smooth, or sorry, piecewise continuous. On the interval 0 to infinity. And exponentially bounded. Then there is some C for which the Laplace transform of the derivative of f is equal to s times the Laplace transform of f minus f of 0. And you'll notice there's no mention of c here yet. Here's where the c comes in. For t greater than c. Sorry, s greater than c, I should say. S greater than c. Okay. So there's a lot of stuff in here that is just there for the lawyers, and then there's the stuff that matters to us. Here's the stuff that matters to us. This formula right here. What this formula is basically telling us is that under the new regime of Laplace transforms, taking a derivative is going to be accomplished merely by multiplying by an s and then subtracting the initial value. So that is going to be our main tool for solving all sorts of initial value problems. So let's write that again. Here's the real takeaway. The real takeaway is that the Laplace transform of the derivative of a function is equal to s times f of s, that's capital F this time, minus f of 0. The key takeaway. All right. Now, we don't prove a lot of things in this class, but this is such a useful formula, and the proof is not super long, so we might as well actually indulge ourselves in a little bit of theorem proving. So let's just start by writing down what it is we're trying to even find here. We're trying to find the Laplace transform of the derivative of f. Okay, well, by definition, what does that even equal? That equals the integral from 0 to infinity e to the negative st times f prime of t dt. Okay, well, how in the world are we going to integrate this, not even knowing what f even equals? Well, if we set up an integration by parts, we can actually get pretty much there. So u equals something, dv equals something. Now, your usual strategy in choosing the u's and the dv's is the biggest piece that you can comfortably anti-differentiate makes a good v, and anything that gets simpler when you take its derivative makes a good u. Now, here, it just so happens that I am staring right at a derivative, so my dv actually kind of suggests itself, make it the derivative that I'm actually looking at. So that means v is going to be just f of t. Interesting. All right, well then that leaves e to the negative st for the u, which means du is going to be, now it's a derivative, so it's going to be negative s e to the negative st. All right, well then integration by parts would take us to u times v, which is f of t e to the negative st. Now that's going 0 and infinity. Sorry, it's minus and then negative. So that's going to be the integral from 0 to infinity of v du, so that's f of t. And I'll just go ahead and pull the s out. This is an integral with respect to t, so pull the s out. That's what made the usual negative into a positive here. Times dt. And now when we look at what this actually is, here we are, so we are dealing with, something that by admission is of exponentially bounded, or also known as of exponential order. So I'll say that sometimes because that's the way I was raised. But exponential order or exponentially bounded are two ways of wording this. And by construction, f is assumed to be of this order. And so, as long as s is above the threshold c that f has for being exponentially bounded, this will be 0. So that's by hypothesis. Minus f of 0 times e to the 0. So that's just going to be f of 0. Plus, and now here, what is this? This actually is just directly the definition of a Laplace transform. So this is s f of s. So what is that equal to? S f of s minus f of 0. So that is, in fact, that's the argument. Now, the only leap that we made here was in assuming that it was exponentially bounded, leading to this this limit equaling 0. But that's it. Okay, well that's all well and good, but how are we going to actually use this? Well, in order to use it, it is usually going to be necessary to look at derivatives higher than just first order. So let's explore that. So higher derivatives. Well, if we go around thinking about just the order n derivative, then that would be f n of t. Then what we've really got here is basically an iterated process where we just stick that formula into that formula into that formula until we recursively reach the end of our stack, and then that will be that. So this is the same thing as the Laplace transform of the derivative of the n minus first derivative. And so, according to our little formula here, this or actually no, that's just so here. This by what we just found is going to equal s times the Laplace transform of f n minus 1 of t minus f n minus 1 at 0, and then just repeat. So we are just recursively going to be repeating this process until we reach the end of our derivatives, and so dot dot dot. And at the end of it, what have we got? We've got, we'll have a power of n onto s, or on the s. Basically, one s will be popping out for every derivative we take, times f of s minus the next power down on the s times times f of 0 minus, so now it's going to be s n minus 2, it's going to be f prime of 0 minus dot dot dot, until we eventually run out of s's and we get down to the penultimate derivative, or actually the ultimate derivative in this writing, so n minus 1 of 0. So the way I like to remember this formula is that we count down s's, count down s, count up derivative. Okay, so then just as an example here, let's say, just an example of how this looks. Let's say that capital X is how we're going to write the Laplace transform of x of t. Then if I'm doing the Laplace transform of, let's say, the third derivative of x, that's going to equal the third power on s times x minus, now the s's count down, the derivatives count up. So s squared, and then it's going to be minus s, and then it's going to be minus just the x. And here, we're just going to be looking at x of 0, x prime of 0, and then x double prime of 0. So that's how this would get implemented. And now, how do we actually make use of this to do our work for us, which is to solve initial value problems? Essentially, here's the idea. The idea is, so take your initial value problem, apply the Laplace transform to both sides. Solve for capital X, the Laplace transform of x, and then apply the inverse Laplace transform to get little x. All right. Short plan, is it going to be so short in implementation? Let's find out. So we're just going to try lots and lots of examples here to get the feel for it. Okay, so let's say we had x double prime plus 9x, and okay, we'll just call this example A. X double prime plus 9x equals 0. That's our differential equation. We'll say x of 0 equals 3, and x prime of 0 is equal to 4. Okay, before doing this, it's useful, or it's worthwhile to note that this is not the only game in town. We could have solved this differential equation, this linear second order homogeneous differential equation, a number of different ways. We could solve it by changing it into a system. We could solve it by just actually doing our techniques for second order homogeneous linear differential equations. But let's see how the Laplace transform looks. So we're going to take the Laplace transform of both sides. Now, as you might predict, the Laplace transform of 0 is just 0. The Laplace transform of x we'll just write with a capital X, and as for this part, there we just use our little formula. So what's it going to be? S squared times x, capital X this time, minus s times x of 0 minus just x prime of 0. So you count down the x's, down the s's, up the derivatives. Plus 9x is equal to 0. All right, well, we have some numbers we can put in here. So we have s squared x minus s times 3 minus 4 plus 9x equals 0. And now we just remember that we're solving this for the capital X. So that means I need to move everything that has the x to one side and factor it out, and everything that doesn't to the other side, and then we can solve. Okay, so what do we have? We have capital X times s squared plus 9 is going to equal 3s minus 4. And if I want to solve that, I just divide. So x equals s squared, 3s minus 4 over s squared plus 9. Now, where do we go from here? Well, we need to eventually try to take the inverse Laplace transform of this, and in order to make that work, it'll be helpful if we break this into the two pieces, the one that has the s and the one that doesn't. So 3s over s squared plus 9 minus 4 times, and here I'll just leave a little space, so I'll make it 1 over s squared plus 9. And now, if I need this to be fit for inverse Laplace transforms, I need the number up here to be the k. So here, k equals 3, I can see that. So what I need is to make this equal k, so I'll need 3s s squared plus 9 minus 3 over s squared plus 9, and to accomplish that, if I'm multiplying by 3, I have to also divide by 3. So 4/3 is how this is going to have to go. And I guess actually I should pull that 3 out. Oh well. Now I can safely take the inverse Laplace transform of both sides, and I'll have 3, and s means cosine. The k here is 3, so it's going to be cosine 3t minus 4/3 sine of 3t. So notice that is the kind of answer we would have gotten by any of our other methods. It just certainly the road there looks pretty different. And it requires us to know the inverse Laplace transforms of such expressions as this. But these are all fresh in our mind from making that table just last section. All right. Well, let's try this again. And now let's go x double prime plus 8x prime plus 15x equals 0, and x of 0 equals 2, x prime of 0 equals negative 3. Okay, step 1, we take the Laplace transform of both sides. So here we go, and as we do this, we're just going to have to think about what it's going to take to execute this Laplace transform. It's going to take that formula that we started this section off with. 0 is also the Laplace transform of 0. Okay, so here, what do we have? It's the second order, so s squared x. Now, count down the s's, count up the derivatives. So s times x of 0 and then minus x prime of 0. Here we have plus 8. We have just the first derivative, so it's going to be s x minus, and we still have an 8. The 8 is in front of everything that comes here. Times x of 0. And over here we'll have 15x equals 0. All right, now remember the goal here. The goal is to solve this for x. And in order to solve this for x, I need to get all the x-related terms together. x times, what have I got? S squared plus 8s plus 15. So that's all the x-related terms, and they are all collected together on the left, and the x has been factored out. And here, I'll move all the other things over. Or actually, I guess one step at a time here. So now I will take the initial conditions, plug them in. So plus 2s, or minus 2s, plus 3, minus 8 times 2, which is 16. So combine those, and it's going to be negative 13, and move it over to the other side, and we get x times s squared plus 8s plus 15 is equal to 2s plus 13, and then we will divide both sides by this, and that will give us x equals 2s plus 13 divided by s squared plus 8s plus 15. And that bottom can be factored. And so what we have is going to be s plus 3 times s plus 5. And what that means is, if we want to break this down into more usable pieces, we'll need to do a partial fractions decomposition here. So 2s plus 13 over s plus 3, s plus 5. That would decompose in a partial fractions way to something over the first factor, s plus 3, plus something over the second factor, b times s plus 5. Well, if I multiply everything through, that's going to take us to 2s plus 13 is equal to a times s plus 5 plus b times s plus 3. Now, if I set s equal to negative 3, so as to isolate just the a, then what will I have here? I'll have negative 6 plus 13 is going to be 7 equals, so if I put that, it's going to be negative 2a. So a equals negative 7 halves. Sorry, it's going to be positive 7 halves. And then if s equals negative 5, then what's that going to equal? So on this side we'll have positive 3, it looks like, and then there won't be an a. And here we're going to have negative 2 times b. And so then that means b is going to equal negative 3 halves. And then that means that our capital X will be 7 halves e to the negative 3t, or 3s, I mean. Get ahead of myself. Getting ahead of myself and mixing everything up. Okay, so capital X is equal to positive 7 halves times 1 over s plus 3 minus 3 halves 1 over s plus 5. Okay, now those of you who had an idea where we were headed can see what I was accidentally mixing up there. I was mishmashing a couple steps together, because our next step here is going to be to take the inverse Laplace transform, and we think about our table, and we recognize this. We recognize these expressions as being specimens from our table, and in particular, what we get is 7 halves e to the negative 3t, that's what this one looks like, minus 3 halves e to the negative 5t. These are known Laplace transforms. In particular, the Laplace transform, remember, of e to the at was found to be 1 over s minus a, and that's the shape of these. Okay, so once again, we got to the same sort of answer that we expect to get in problems like this. The process, though, is a little unusual. Not the sort of thing that we would typically have seen along the way in producing that answer. All right, well, let's try another one. This time, let's have it not be homogeneous. So now we are getting into the place where the examples start to get a little harder by our traditional methods, and we can see how this will compare. So x double prime plus 4x equals cosine t, and we'll just have initial conditions x of 0 equals 0, x prime of 0 also equals 0. All right, so if we wanted to do this by the methods that we have already in our arsenal, that's going to involve having to do, say, complexification, for example, or the method of undetermined coefficients. And neither one of those is going to be particularly pleasant. So let's see what the Laplace transform has to offer us. So we start by just taking the Laplace transform of everything. And so what we're going to have here, since it's second order, it's going to be s squared x minus, now the s's count down and the x primes count up. So s times x of 0 minus just x prime of 0 minus 4 capital X. And this is going to equal, now here this is cosine, which means we're going to have a k. Oh, sorry, but it's backwards, so it's going to be s. Divided by s squared plus k squared, plus, because it's t for trig. So s over s squared plus 1. All right, what do we have? These are going to each equal 0, so it's going to be s squared x minus 4x equals s over s squared plus 1, which means x times s squared minus 4 equals s over s squared plus 1. Oh, sorry, this was plus right here, plus right here, plus right here. So then x is going to equal s divided by s squared plus 4, s squared plus 1. All right, well, back to partial fractions. So it's going to be some mystery over s squared plus 4 plus another mystery over s squared plus 1. Now, if these were only linear, I could just use a and b like that, but because they are degree 2, and that's why I'm actually going to change the letter here, I don't like to call that b, I have to go as plus b, and I have to go cs plus d over here. And it's because of the square in the bottom. So this is one of the extra little exceptions for partial fractions that you may recall. Okay, well then that means S is equal to AS plus B times S squared plus 1 plus CS plus D times S squared plus 4. Now, what a lot of people who do this a lot like to do in these cases is actually continue the process of just plugging in useful values to make the numbers disappear. Unfortunately, though, to make that happen, that's going to require complex numbers, and so it's not actually that convenient. So, what we'll do is we'll just multiply it all out and then combine, or and then just collect all the like terms. So we have AS to the third plus AS plus BS squared plus B plus CS to the third plus 4CS plus DS squared plus 4D. So then, if we just look at the pieces, the S to the third terms, it's going to be A plus C, and there's none on the other side. So A plus C equals 0. So just as a note, that means A equals negative C, for example. S squared, what's that? Looks like B plus D on one side, nothing on the other. So just as a note, that means B equals negative D, again, just something to keep in mind. Now for the S side of things, what do we have? We have A plus 4C equals 1. So what does that give us then? It looks like, so we have A plus 4C equals 1. So then if I take this would be negative C plus 4C equals 1, so 3C equals 1, so C equals 1/3. So that means A equals negative 1/3. Nice to see that happen. And then for the constant, what do we have? We have B plus 4D equals 0. So in other words, negative D plus 4D equals 0. And so then 3D equals 0, D equals 0, so B also equals 0. So then, what does that give us? That gives us that the capital X is equal to, let's see, so what was the A here? The A was equal the A, so sorry, it's just like last time I did this example, I had the roles of A and B switched with C and D, and I had A and B over the S squared plus 1. So I was just making sure that the discrepancy was accounted for by that. And so we have negative 1/3 S over S squared plus 4 plus 1/3 S over S squared plus 1, which means then we are looking at something that fits in our pattern. So remember what the Laplace transform of cosine kt was. It is S over S squared plus k squared, which fits exactly. So this is going to equal negative 1/3 cosine 2t plus 1/3 cosine t. So that's how that goes. Now this is something. It's a note that has come up already in use, but it's just kind of a useful fact that we will make frequent recourse to. So it's good to remind ourselves about it. So note the Laplace transform of just a t, e to the AT. This is one of the most commonly occurring ones that was not usually included on the most elementary tables. So this is equal to 1 over s minus a squared. It's just a nice little note, and if you want to see how the actual proof of this can be made, because we have this is actually a consequence of a formula that we gave, but it's not a formula that we proved. So if you do want something that will put it on firmer footing, what we can see is we'll just look at the actual integral itself. So e to the negative st, just because it's a nice illustration of how integration by parts works when you have three factors here. T e to the at dt. So the way to make it work is to combine these two together. So 0 to infinity. And what are we going to have? We're going to have t, and then we're going to have e to the negative st times e to the at. So then we can factor out the t, and that's going to be a minus s dt. And now we are ready for some integration by parts with u equals t as usual, du equals dt. Again, pretty much as usual. dv is going to equal the e to the t a minus s dt, and then v is going to equal 1 over a minus s e to the t a minus s. And then in actual practice, this is going to end up being uv. That's going to be t times 1 over a minus s e to the t a minus s 0 to infinity minus the integral of v du. So I can pull out the thing that has nothing to do with t, so that's the a minus s part. And then we have e to the t a minus s dt. This is the integral from 0 to infinity. Alright, so now when we plug in the 0 and we plug in the infinity, we have once again the situation that leads to it equaling 0 when we plug in the infinity, and that's whenever s is less than a, or sorry, s is greater than a. So this equals 0, and that's when s is greater than a, minus, and then when we plug in 0, it's going to be another 0. And then what we're going to have over here is going to be minus 1 over a minus s times 1 over a minus s times e to the t a minus s, and this is going to be plugging in 0 and infinity. And so what's this going to equal? It's going to equal negative 1 over a minus s squared, and this is going to equal, when we plug in infinity, it's going to equal 0 as usual, minus 1 when we plug in 0 for t. So we get 1 over a minus s squared But it's just a nice little fact. It's usually written the other way because most of the formulas end up coming out that way. And when you have something squared, you can change it to its opposite without consequence because the square will cancel the negative. So anything that is a difference squared can be reordered in this way. Okay, now why do that? Because every once in a while it's going to come in a lot of handy, and when it does, boy oh boy, is it going to be nice to have that on our docket. So let's try another of the example series here, and this is going to be now just up to example whatever we're on now, D. So for example, D, what we're going to take is this. So let's go x double prime plus 3x prime plus 2x just equals t. And we're going to do x of 0 equals 0, x prime of 0 equals 2. All right, well, we start it the usual way by taking the Laplace transform of both sides and seeing what happens. Oops, plus. All right, so here we get the usual thing, s squared minus s x of 0 minus x prime of 0. Here, what are we going to get? Plus 3s, sorry, s squared x, 3s x minus 3 x of 0 plus 2x. That's going to equal 1 over s squared. So this is on our table. It's famous Laplace transform. Okay, so now what's this going to equal? Put in all the initial conditions here. So it's going to be 0 minus 2 plus 3sx minus 0 plus 2x. Now, what is that going to give us? It looks like that is going to be equal to s squared plus 3s plus 2 times x is going to equal 1 over s squared plus 2. If I move everything that didn't have the x on it to the other side, and then if I divide everything by this, then I will have x squared, sorry, capital X, equal to 1 over s squared times s squared plus 3s plus 2 plus 2 over s squared plus 3s plus 2. Which I can then, if I want, I can combine these so that they have a common denominator that will allow me to do better partial fractions. And so what I'll have is 2s squared plus 1 on the top divided by s squared plus 3s plus 2. Now, there are other fancy techniques that can be done, by the way, for expressions like this, which are which are similar to things that we already can work with, but have extra factors of s squared in their denominator, but they are a little bit above our head right now. So what we'll just do is do what we have been doing, which is partial fractions. So 2s squared plus 1, s squared plus 3s plus 2. This is equal to something over the s squared. Now what we have to think about is what variation of partial fractions are we going to need to use here. Oh, actually, before we do that, might as well factor the part of this that we can factor. 2s squared plus 1, s squared, s plus 1, s plus 2. Yeah, sorry. That'll be better. That'll be better. Otherwise, we're just going to end up with the classic situation of having lots and lots of extra variables. Okay. So now what we have is 2s plus 1, so 2s squared plus 1 over s squared times s plus 1 times s plus 2. That's going to equal some mystery a over s squared, and now we have to think about what it is we have to do when one of our factors is like this. So when you have a repeated factor in your partial fractions, what that means is you need to include more terms with just a single coefficient on top of ever decreasing powers of that repeated factor. If you have an irreducible quadratic, then that's when you need the as plus b situation. And then this is going to be c over s plus 1, and this is going to be plus d times s plus 2. All right, so now what is that going to give us? So if we multiply everything by what it takes to clear away all the denominators there, we're going to have 2s squared plus 1 is equal to a times, and it's going to be the s plus 1, s plus 2. We're going to have b times s plus 1, s plus 2. We're going to have c times s times s plus 2. And we're going to have d times s squared. S squared and s plus 1. All right. So then, if we want to take the pieces of this and try to find the values, we can look for some strategic values we can make. So s equals 0 would be a nice one. So what's that going to give us? It's going to give us 1 on the left. It's going to give us a times 1 times 2. So a times 2. Now the rest will equal 0. So that gives us immediately a equals 1/2. That's nice. And let's look for what else we can immediately find. If we set s equal to -1, that cancels everything except for the c term. So what's that going to be? It looks like it's going to be 3 on the left. That'll be 0. A will be 0. The a term will be 0. The b term will be 0. The c term will survive. That's going to be c times -1 squared, which is 1, times s plus 2, which would also be 1. That means c equals 3. Let's see, what else can we do? How about s equals -2? So s equals -2. So that's going to give us 2 squared times 2 is 8, plus 1 is 9. So 9 equals And now every term is going to disappear from this except the one that has the d. So it's going to be d times 4 times negative 1. So d is going to equal negative 9/4, it looks like. And now, as for the b term, unfortunately, we've come to the end of the line on our ability to keep with this process because we have exhausted all of the factors that that can be essentially isolated in order to make the variable purely visible. So if we can't use that same method here, what we can do is look for the easiest term to get a straight answer for b out of, and that'll be the highest degree term typically. So we'll just look at the s cubed terms. There's none on the left. On the right, the s cubed is going to come from just the highest degree factors all multiplying together in each one. And there won't be one over here. It's going to be as squared will be the highest one. Here it'll be highest degrees all multiplied together. So bs times s is going to be b s to the third. Here c s to the third. And here d s to the third as well. Well, we have numbers for all of these. And so b plus c plus d equals 0. So 0 equals mystery b plus the c, which was 3, minus 9/4. And so what does that equal to? So 3 minus 9/4 is going to equal, so it's 12/4 minus 9/4 is b plus 3/4. So b equals negative 3/4. So we put the pieces together and we've got our x. So then capital X is equal to, what's it equal to? It's equal to a over s squared, or times 1 over s squared, plus b, negative 3/4, times 1 over s, plus c, times 1 over s plus 1, plus d, negative 9/4, 1 over s plus 2. Now, all of these can be directly translated back into the pre-Laplace Transform versions of them because they all belong to our table. So 1/2 s squared, that's going to be a 1/2, and this is actually, if you recall, just t. Here we're going to have negative 3/4 and 1 over s, that's the Laplace transform of just 1, plus 3 times e to the negative 1t minus 9/4 e to the negative 2t. So that's how that will go. And then one last twist on this is that we can use a very similar method for systems. And the tool that we're going to use is a tool that we have used a couple times already. It's a tool that keeps on giving. It's from linear algebra, and it's the 2x2 Kramers rule. So if what we have is something of the form a, b, c, and d times x1, x2, that's equal to e, f, And remember how Kramers rule works. We can get the actual solutions right away by just cutting straight to this expression. The determinant of EF in place of the first column of our matrix, BD, divided by the determinant of the original matrix, A, B, C, and D, and then X2. A and C are where they're supposed to be, and then E and F are swapped in for the second column. And again, in the denominator, we just have the original, A, B, C, and D. And then we can actually just take those determinants and solve our systems from there. Now, is this as easy to do as it is to say? No, not really. As is frequently the case in Laplace transforms, the idea is not so bad. The execution is where they get you. So let's try an example of this. And for example, let's just take the system x prime is equal to x plus 2y, and y prime is equal to x plus e to the negative t, and we'll just take some very straightforward initial conditions, x of 0, y of 0, each equals 0. Okay, so this is a system that is a little bit outside of our wheelhouse from before, because it is not an autonomous system. We have this little piece that involves a t, which is not something we have typically seen. Well, how do we go about this? Turns out not so differently from the way we've gone about these types of things before. So x prime equals x plus 2y. Y prime equals x plus e to the negative t. What we'll just do is take the Laplace transform of both sides of each of these equations, and we will create then a system of equations that we can solve for the capital X and capital Y using Kramers rule. So the Laplace transform x prime is equal to Laplace transform of x plus Laplace transform of 2y. Here, the Laplace transform of y prime is equal to Laplace transform of x plus the Laplace transform of e to the negative t. Alright, and we follow each of these where they lead us. So this is going to be s times capital X minus x of 0 is going to equal capital X plus 2 times capital Y. Over here, we're going to have s times capital Y minus y of 0 is equal to capital X. Here, this is k, or this is where a equals negative 1, so this is going to be plus 1 over, so it's s minus a, so s plus 1. That's what we'll have over there. But since our initial conditions were x of 0 equals 0, y of 0 equals 0, that takes us to this. So we've got is sx equals x plus 2y. And over here we've got sy equals x plus 1 over s plus 1. And so if I want to make this fit a little bit better into the framework of Kramers rule, I need to collect all my variables on the same side. And in particular, I'm going to move them over to the left here. So what I have then is s minus 1 times x minus 2y equals 0. Whereas over here, I'll have negative x plus s times y equals 1 over s plus 1. And so if I then want to turn this into a matrix, it's going to be a matrix s plus 1, negative 2, negative 1, s times x and y is going to equal then 0 and 1 over s plus 1. And so then, according to Kramers rule, I can actually get the x by just taking the determinant 0, 1 over s plus 1, negative 2s divided by original determinant, s plus 1, negative 2, and then down here, negative 1 and s. So let's actually figure this out. So to get the determinant, you would do a typical this times this minus this times this. And so what we're going to have is just going to be 0 plus 2 over s plus 1. Down here, we're going to have s times s plus 1 minus minus minus, so it's going to be minus 2. Oh, hold on. Quick note. Over here, this was s minus 1, s minus 1, s minus 1 right there. S minus 1. Okay. Okay, so anyway, so what's this going to equal? It's going to be 2 over s plus 1. And down here, what are we going to have? S squared minus s minus 2, which we can then write as 2 over s plus 1. And this actually factors into s plus 1, s minus 2, so it's going to be s plus 1 squared, s minus 2. Okay, so there's capital X. All we have to do is find its inverse Laplace transform. Okay, how about capital Y? Same basic thing, just swapped into the second column now. So it's s minus 1, 0, negative 1, 1 over s plus 1. Divided by original, so s minus 1, negative 2, negative 1, and s. Okay, so what are we going to have here? We're going to have s minus 1 divided by s plus 1, and then minus 0 for the top. For the bottom, we're going to have s times s minus 1, minus 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 is minus 2. And so, by the same token really as before, we're going to have s minus 1 divided by s plus 1 times s squared minus s minus 2, which is going to be s minus 1, divided by s plus 1 squared s minus 2. All right, well, now we've got our x and our y capital, but we don't have them yet in a form that's going to be convenient for inverse Laplace transform finding. So let's figure out how to decompose them using partial fractions to get what we need here. All right, so partial fractions will tell us that if our x starts off by being equal to 2 over s plus 1 squared s minus 2, then I can try to decompose them and think about what version of partial fractions this is going to be. So s plus 1 squared, since we have a squared factor in the denominator here, that means what we need is to duplicate this term with the different powers of s plus 1. And then the other one is just going to be c over s minus 2, and that's going to equal just 2 over all of these factors, s plus 1 squared s minus 2. All right, well, what's that going to mean? That's going to mean a times, looks like it's just going to be s minus 2 plus b times s plus 1 s minus 2 plus c times s plus 1 squared just equals 2. So we can choose some strategic values for s here, like s equals -1. It's a good value. And that's going to give us, so it's going to be -3a. It's going to be the only surviving term on the left, equals 2, which gives us a equals -2/3. Let's see what else we can do. We can set s equal to 2, and then only the c term will survive, so we're going to have 2 plus 1 squared, so that'll be 9 equals 2, so c equals 2/9. Now, as for the b, the easiest thing here is going to be just to use the s squared terms. So the s squared terms here, there's not going to be one from the first one. It's going to be b s squared plus c s squared equals 0. So b equals -c, so that means b equals -2/9. So that gives us our x is equal to -2/3 times 1 over s plus 1 squared plus 2/9 times 1 over s plus 1 plus, oops, sorry, this one was -2/9. And then this one is plus 2/9 times 1 over s minus 2. Okay. Now, before we take the inverse Laplace transform of that, let's deal with the y. So the y that we had here, capital Y, was equal to s minus 1 on the top, divided by s plus 1 squared s minus 2. So we're going to have pretty much the same sort of decomposition as we had before. We're going to have a over s plus 1 squared, b over s plus 1, and c over s minus 2, only this time it's going to just equal s minus 1 over s plus 1 squared, s minus 2. Alright, well, once again, the decomposition is going to go along these lines. A times s minus 2 plus b times s plus 1, s minus 2, plus c times s plus 1 squared. Now that's going to equal just s minus 1. So I set strategic values for my a, or I mean for my s. S can equal, to begin with, -1. And that's going to cancel everything but the a term on the left. So it's going to be a times 3 equals, looks like it's going to be -2. So actually it's going to be -3 right here, right? -1 minus 2. Okay. So then a equals -2 over -3, so 2/3. S equals 2 seems like a nice value to try. Everything cancels except for the c term, so it's going to be c times 3 squared, so it's going to be 9. Is going to equal 2 minus 1 is going to be 2. Sorry, 1. 1. I can do differential equations, but I can't subtract. All right. So then, what's that going to mean? Then c equals 1/9. All right. And now, once again, we are not going to be able to repeat the same process for the b term because there are no factors that are uniquely missing from b. But what we can do is take the highest degree term, take the s squared, so it's going to be b s squared plus c s squared, and there is no s squared on the right. So then b equals -c, so then that means b equals -1/9. So then that means that our y is going to equal 2/3, 1 over s plus 1 squared, plus 1/9, no, sorry, -1/9, -1/9. This one is just 1 over s plus 1. And then here's the plus 1/9. Plus 1/9, 1 over s minus 2. All right, so then we can do the inverse Laplace transforms to get the little x and the little y. So for the x that we had here, so if capital X is -2/3, just remind you what it was, -2/3, 1 over s plus 1 squared, minus 2/9, 1 over s plus 1, plus 2/9, 1 over s minus 2. Then, if I want the inverse Laplace transform, I just have to look up on the table that we have of all the useful values of Laplace transforms, and we would see this is -2/3. This is what you get when it's t e to the at, where a here is going to be -1. Minus 2/9. This is just going to be e to the -t. There's no extra factor of t. And then plus 2/9 e to the 2t. And now for the y, for little y, we have very similar things. The first term was just positive 2/3 instead of negative 2/3, so it would be positive 2/3 t e to the negative t minus 1/9 e to the negative t plus 1/9 e to the 2t. So that would be that. Alright everyone, so now that we have got that under our belts, let's look at one more specific category, and this, because this is being recorded a little bit afterwards, and this is actually a new video, we are going to call an appendix. And this has to do with a category of function that's going to be particularly useful for us in the upcoming section when we start getting into some fancier things like circuits and springs and things of that nature. And so we'll call this the appendix. The appendix to 6.3, and the topic of this is going to be shifted unit step functions. All right. So here's the idea. The idea is that we can delay a function by using the unit step function and its variations. So we can put quotes on that, delay a function by using u of t and a horizontal shift. So what that looks like is, let's just say we have some function, a very basic function, like just f of t looks like that. And let's say that we want to actually delay it by a unit. So it does this thing, same thing, goes up in that same linear fashion, but a units later than before. And let's say we wanted to call that g of t. And here, the way we could actually accomplish this is, let's say this is a unit. So essentially, we put in the unit step function, u sub a of t, or u of t minus a, same thing. And that basically multiplies it by 0 until we get to a. And now you might think, okay, so now once it reaches a, then it's time for f to kick into gear. And you'd be right. However, at the point where t equals a, we should only be mimicking the behavior of this one when t equals 0. So essentially what we have to do is make that t minus a. So this gives us an alternative to piecewise formulations. And is more suited to Laplace transforms. So the reason why it's more suited for Laplace transforms is that there is actually a relatively simple adjustment that you can do to a Laplace transform to incorporate this shift. So here's the reason. The reason for doing this. And I'm not going to prove this Laplace transform formula, although it is not difficult to do so. It would actually follow pretty directly from the definition of the Laplace transform and just say like a little substitution in the integral. It wouldn't be very difficult to do so. It's just this video and the other videos in this section are running a little long, and we just don't have time to prove every little Laplace transform property. So the reason for doing this is the following pair of identities. So the Laplace transform of something of this form, u a of t f t minus a, that's equal to e to the negative as capital F of s. So whatever the Laplace transform was going to be of the basic function f here, it's that same thing, but with an extra factor of e to the negative as in front. And then the reverse side of this same process is that if we are taking the inverse Laplace transform of something that looks like what we have on the right here, so the inverse Laplace transform of e to the negative as f of s, then that will just be the thing that we have over here. So u sub a of t, f of t minus a. Now, once again, like I said, this is not actually difficult to prove, and I welcome any of you wishing to prove it, and if you have any questions about how to prove it, feel free to ask me. But at a certain point, when we start running out of time, we have to start taking more things on faith than we would ordinarily be completely comfortable doing. And one of the most invaluable resources in any mathematician, engineer, or physicist's toolkit is a comprehensive table of Laplace transform formulas. So here is actually is in the front cover of what used to be the textbook for this course. Is a very comprehensive table of Laplace transform formulas, and this is also available on D2L under the content for this course. It's an extremely useful resource and one that I recommend you use copiously. You should do almost all Laplace transform problems with one finger on the table of Laplace transforms and the other finger on the paper that you're doing the work on. It's something that you will always want to have ready access to because a lot of formulas look similar, and no matter how deeply you understand it at a given point in time, you will want the resource for a different point in time later on. And now this is the formula, and it's to be found on that table. But how do you actually use the formula? So let's just discuss how to use this. All right, so basically, step one is to rewrite whatever you have in whatever form it is. Maybe it's a graph, maybe it's a piecewise defined function. Rewrite that as combinations of terms of this basic format. So rewrite the function in the format. So u sub a t f t minus a. So the important thing here is that for the second factor here, you do not just see a t anywhere. Every t is replaced by a t minus a. So every t. t minus a. And there may, and in fact there usually will, be multiple terms of this form. Okay? And then, after that, you apply the formula. Alright, so then at this point, once you have rewritten it in this form, and this may require some creative rewriting, just a note. Then after that, what you do is you apply the formulas to get f of s, and then if what you're doing is an initial value problem or a differential equation, which is likely considering what class this is, so if solving an initial value problem, then the next step would be solve for x and apply the inverse formula. All right, well, enough talk. Let's try this for an actual example, and the actual example will just be a differential equation where x prime equals f of t, x of 0 equals 0, where f of t is the function depicted below. And so the way it's going to look is it's going to be nothing, 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 nothing until t equals 2. And then what it's just going to be is basically a little line segment, and we'll just say slope of 1, this is 2, 3, and this is just a slope of 1, so that means that that y value would just be 1 there, or I guess x value, technically, since this is t. And so essentially what we have is a shifted and trimmed version of just t. So this is a shifted and trimmed g of t equals t, or h of t equals t. Just something equals t. I don't want to be confusing and say f of t equals t. So it's shifted and trimmed. So now step 1 here, we have to rewrite this in the approved format so that we can actually do something here. And here's one way of doing it. So essentially, you can just take, you can take a couple steps to do this, but one way you can do this is essentially you can take t minus 2, so this does the shift, and then essentially you turn it on at 2 units, and then you turn it off at 3 units. So this turns on. At t equals 2, and this turns it off. at t equals 3. So if you look at what's happening here, essentially it is nothing, nothing, nothing until t equals 2. That's when u of 2 kicks into gear, becomes equal to 1. And then it's nothing, nothing, nothing for a while, or sorry, then it's 1, 1, 1, 1, 1, and then it's 1 minus 1 from 3 on. So basically it cancels it out. Now that's all well and good, but it doesn't fit our format. So what we can do is rewrite it by distributing somewhat here. T minus 2 minus u3 of t times t minus 2. Now this one is all perfectly approved. This is in the format. This is exactly in the format that we wanted. So shifted. This is just a shifted t. This one, however, does not quite fit our format because there's a mismatch here. So we want this. We want to see t minus 3 instead of t minus 2. So what you do is you just rewrite it so that you literally can see with your eye a t minus 3. So this term was fine. No objection here. This one, though, is now t, and we want to see t minus 3, but in order to make that happen, I essentially had to subtract 1, so to balance the book, so I have to now add 1. So t minus 3 plus 1. Because I needed to be looking at literally a t minus 3 there. So now this is just still a shifted t, but this one has become now a shifted t plus 1. If you look here, plus 1. Whereas this was just t replaced by t minus 2. This is t plus 1 with t replaced by t minus 3. Takes a little getting used to, but that's the basic operation there. All right, well then, back to the differential equation at hand. So then, if x prime is equal to that, so u2 of t times t minus 2, u3 of t, and by the way, you could, if you wished, distribute this, but I don't see any real advantage to doing that. T minus 3 plus 1. And now we do what we do, which is apply the Laplace transform to both sides of this in order to get the usual Sx minus x of 0, which here just is equal to 0 by our initial condition, is equal to, now right here, what do we have? That's going to be, so a is going to equal 2. So that means we have a to the negative 2s times the, and this is just basically a shifted version of t. So the Laplace transform of just t by itself would have been 1 over s squared. Minus, same thing here, e to the negative 3s now. And now we just look to what the Laplace transform of the sort of the function like absent the shift would have been, which would be t plus 1 in this case. And so that is going to be Laplace transform of t plus the Laplace transform of 1. So it's going to be s squared, and then plus 1 over s. Okay, so now cleaning this up a little bit, we have little s, big X, so the Laplace transform of X. And I'll just keep that the form it is. Minus, and then we just keep on going here, e to the minus 3s times 1 over s squared minus e to the negative 3s. At this point, for no particularly good reason, I've just decided I'm going to distribute it all out, have 3 terms. I could just as easily keep it still as 2 terms. It would be fine either way. But now, I just continue solving for the x. So that would involve here dividing by the s, which would mean we've got e to the negative 2s, 1 over s to the third, minus now e to the negative 3s, 1 over s to the third, and then for the last term here, e to the negative 3s is 1 over s squared. Okay, so be it. And now we want to do the inverse Laplace transform of this to get back to x. So here, we just take that formula. So the reason for doing this here, the whole reason for doing this is that we've got this little bridge that takes us back and forth between the forms that we see here and what we have over here. And I guess technically I better clean this up just a little bit for the purposes of taking the inverse Laplace transform, just to make life easier on us after this hard day of solving. So here, if I wanted this to fit in the format that is easy to take the inverse Laplace transform of, I would want there to be ideally a 2 on the top. So it's 2 plus 1. And that's just going to be, in order to balance the books, times 1/2. Minus e to the negative 3s. And again, here, if I wanted this to be 2 s to the 2 plus 1 times 1/2. And then for the last term here, 1 over s squared, that's already a known Laplace transform of just t. So I won't have to make any change there. I just wanted this to fit the exact format of a Laplace transform that I knew, and now it does. And so that means now I can apply this. Little rubric here, and what's it going to be? So, yep, fits exactly. So here, I will just be taking the unit step function shifted by 2 units of t times 1/2, and then this now exactly fits the format for the inverse Laplace transform of t squared. Oops, but don't forget, this is not just u sub a times t, or sorry, f of t, it's f of t minus a. So whatever I thought the formula was about to be, make it a t minus 2 instead. Okay, so now what do we have here? This is going to be the same thing, but u sub 3 of t times 1/2 is t minus 3 squared. And then for this last part here, we have u sub 3 times it would have been just t, but because of the shift, it's t minus 3. All right, so that's what that looks like. Now let's actually look at what it really literally looks like. So let's have a quick check-in on Desmos to see if this makes sense. All right, now as you can see, here I am at Desmos, the best way to see these things in action, and let's try to actually represent the function first off that we're talking about here, and then the function that represents the solution to our differential equation. So the best way to do these types of things is typically to start off by defining the unit step function as a piecewise function in Desmos. And the format for a piecewise function in Desmos is you start by defining the condition on the variable, and then colon, and then what the formula for the variable is supposed to be. So here for the unit step function, we are supposed to have a value of 0 until t equals 0, and then comma, and then you enter in the next formula. So you start with the condition. So t is greater than or equal. So greater than or equal to, you do greater than, and then literally if you type equal, it changes it into equals 0. And then here, actually, that was already looking pretty good. And now there it is. It is, as advertised, the unit step function. It steps up 1 unit, and that happens when t equals 0. So yep, it's a unit step function, all right. I'd know it anywhere. All right, well, now let's actually define the f of t that we thought we had constructed by our little algebraic trickery. And the first way that we wrote it, remember, was u2 of t minus u3 of t all times t minus 2. So let's have a look at that. So you can't do u sub 2. Desmos doesn't understand that notation, common though it is. So the way you do that is you do a literal shift u t minus 2. Okay, so there's that. So notice what that did was that gave a shift over of 2 units of the unit step function that we know and love, and then times u of t minus 3. So that if we look over here, what that does is it basically defines this factor to equal 1 on the window between 2 and 3 and 0 outside of that. And then here, if we just put t, which would be kind of the natural thing to do, here's the problem. It doesn't fit our function. It was supposed to be, our function is supposed to be just a shifted version of just like f of t equals t. So this does not incorporate the shift properly. And so what you have to do is t minus 2. And so there, what we have is a function that is 0, 0, 0, 0, 0, and then it behaves like a shifted version of just the function t, like the identity function, and then after that it turns off. So then it goes back to 0. Okay, so that is the function that we were attempting to create through our use of this unit step function. Now let's make sure that our modified version of it still makes sense. So here's the one that we actually applied the Laplace transform to. So we did that. And then over here, what we had was t minus 3 plus 1. So that was the new version that we made, and it should look exactly the same. If we haven't done anything that actually changed the values, which we hopefully didn't, should look the exact same. And sure enough, it does. Okay, now let's just graph our solution here, which is we'll just call g of t just to give it a different name. So our solution was u2, so that would be u t minus 2 times 1/2. Oops, let's go times 1/2 parentheses t minus 2 squared. All right, and then minus u of t minus 3. That represents the u sub 3. We have again times 1/2. Now it's t minus 3 squared. And then minus the last term, which was u t minus 3 times t minus 3. Okay, So let's quickly look at this and look at the original and see if it makes sense. So the differential equation that we originally created said x prime equals this. So in other words, what we're looking at right here is a graph of the antiderivative of our function. Okay, so the function that we have made should have this as its derivative, in other words. So now we look at the function that we made. What is the derivative of this function? Well, it's 0, 0, 0, 0, 0, 0 for a long, long time. And then here we start to see what looks like a parabola. And if you remember parabolas in particular, this one has the approximate shape of x squared over 2, because it's just a shifted version of that. That would have a derivative that was just equal to t. So, so here we have the derivative we're supposed to have until 3 when the derivative equals 0 again, just as this foretells. So, so does this match the function that we were given to start with? Yes, it does. All right, so there's a little bit of validation. Why would we be interested in functions of this kind of nature? Well, like I said before, this is the kind of function that you encounter when you go about the business of examining circuits. Circuits frequently turn on, turn off, they are opened, they are closed, they have a function that is dependent on time and radically changes nature. Now, piecewise defined functions are something that you can do Laplace transforms of, but it becomes a little bit more convenient to reformulate these things in this format so that we can use these formulas in order to apply these. So that's what's in store for us in the next section: circuits, springs, and the use of this approach to Laplace transforms. All right. Well, till then, I'll see you later. Thank you for joining me for this episode of Math 256. Bye.